Okay, in this video we're going to look at graphing polynomials using calculus techniques. So we'll just look at this example. It's a fourth degree polynomial, which we're going to graph by finding these five things. So we're going to find intercepts, so that would include both the x and y, the intervals of increase, decrease, and the local maximum and min values, and the intervals of concavity and points of inflection. So when you do this, you'll notice that you're basically doing an analysis on three functions. The intercepts, that will come from looking at f at x. The intervals of increase and decrease and maximum and minimum points, that'll come from f prime at x. And the concavity and points of inflection, that will come from f double prime at x, or the second derivative. Okay, so let's just go through this example. So first we will find the intercepts. So we'll go with x intercepts first. So in order to figure out the x-intercepts, you'll take the function f at x, set it equal to 0. So it's x to the 4 minus 4x cubed. So we solve that by factoring. There's a common factor of x cubed. And you have x minus 4. So x cubed equals 0, or x minus 4 equals 0, which would mean x equals 4, or x equals 0. So therefore, x equals 0 and x equals 4 are the x-intercepts. You're also going to want your y-intercept. So your y-intercept, well in this case, because x equals 0 is an x-intercept, y equals 0 would be a y-intercept, but generally you find that by evaluating the function at 0. So that would be 0 to the power of 4 minus 4 times 0 cubed, which is of course 0. So therefore y equals 0 is the y-intercept. So that's our intercept. So that's the analysis that we do on the original function. Now we're going to look for intervals of increase, decrease. So in order to do that, we have to take the first derivative. So f prime at x is equal to 4x cubed minus 12x squared. To get the intervals of increase and decrease, you're going to set that equal to 0. So a factor of 4x squared, and have x minus 12. So 4x squared is equal to 0, which means x equals 0, or x minus 12 equals 0, which means x is equal to 12. Oh, sorry. This was a 3. So it'd be a 3. So x is equal to 3. So these are critical numbers. So therefore x equals 0 and x equals 3 are critical numbers. So to figure out the intervals of increase and decrease, we will do our first derivative test. So minus infinity to 0. Zero to 3, 3 to infinity, and then we're going to look at the sign of f prime. So just taking a value of x in this interval and subbing it into the first derivative would give us a negative number. In this interval we'd get a negative number, and here we'd get a positive. So we have decreasing interval decreasing interval, and an increasing interval. So therefore, f at x is decreasing if x is in the interval from minus infinity to, and I was going to go all the way to positive 3, because you're going to put these two intervals together, and f at x is increasing if x is in the interval from 3 to infinity. So the next thing you look at is the local maximum and minimum point, and we can see from the first derivative test that there's a minimum when x equals 3. So we need to figure out what is the value of f when x is equal to 3. Going back to the original function, that would be 3 to the power of 4 minus 4 times 3 to the power of 3, which would be 81 minus 4 times 27, or 81 minus 104, which would be minus 25. So therefore, there is a minimum at 3 minus 25. So now we'll go on to the concavity. So we're going to look at the second derivative. The first derivative was 4x cubed minus 12x squared. So we're going to have 12x squared minus 24x. So we'll set that equal to 0. Factor 12x. And we're going to get 12x times x minus 2, which means 12x equals 0, or x minus 2 equals 0, which would be x equals 2, or x equals 0. So now we'll do our test for concavity, which looks a lot like the first derivative test, except we're using different intervals. So we're going to go from minus infinity to 0, 0 to 2, and 2 to infinity. And we're looking at the sign of the second derivative, which is right here. So if we took a number between minus infinity and 0 and substituted it into this equation, we would get a positive number, a negative number, and a positive number, which means concave up, concave down, and concave up. So therefore, f at x is concave up if x is in the interval from minus infinity to 0, or 2 to infinity, and concave down if x is in the interval from 0 to 2. And the points of inflection are going to occur at the points where you switch concavity. So that would be here at x equals 0, and then here at x equals 2. So we need to find the y values there. So f at 0, we already know that's equal to 0. That was an x-intercept. And f at 2, we're going to have to evaluate the function. Remember, it was x to the power of 4, so that's 2 to the power of 4 minus, the function was 4 times x to the power of 3, so that'd be 2 to the power of 3, so you'd have 16 minus 4 times 8, which would be 16 minus 32, which would be minus 16. So therefore, there are points of inflection at 0, 0 and 2, minus 16. So now what we need to do is graph the function. So you're going to set up your axis, or axes, and the first thing you're going to do is plot all the key points. So there's 3 sets of key points. You have your intercepts, so your x-intercepts, if we remember, that was 0, 0, and going back to the top, 4, so 4, 0. You have your y-intercept, which was 0, 0, so that's not a different point. You have your max, which there was none, and your min, which was right here, 3 minus 25. And then you have your points of inflection. Which we had 2. One was 0, 0 again, and then the other one was 2 minus 16. Okay, so we just need to graph these. What is it? 1, 2, 3. We have 4 key points. So we need to make a scale. So you want to scale for your x, which will allow us to graph the point 0, 4, 3, and 2. So going up by ones makes sense here. So it'll be 1, 2, 3, 4. And now my y values, I get as low as negative 25. So maybe going by 5s would be good. So this will be negative 5, negative 10, 15, 20, 25, which gets me to my minimum value. So now I'll put all the x-intercepts. So I have 0, 0, and 4, 0. My y-intercept's already on there. There was no max. There's a min at 3 minus 25. So that's down here. I'll label it 2. And then I have a point of inflection at 2 minus 16, which is right around there. So now I just need to basically connect these dots, but in the right way. So I'd look at my points of inflection, or sorry, my intervals of concavity. So I know I go concave up to concave down to concave up. So I'm concave up until 0. So I'm going to draw a graph concave up. Then it switches to concave down till it gets to this point. So it should be smooth kind of transition there. And then it goes to concave up, hits this minimum value, changes to increasing, and it stays concave up the whole way after that. So the graph would look something like that. And that is how you graph a polynomial function.